Hello, welcome to the screencast version of PETE&C's 3D Printers Hard to Build, Maybe Not session. My name is Jim Chronister, and if you're considering building a 3D printer or trying to build one from a kit, hopefully this session will give you some helpful information. First off, if you found this screencast already, you've probably found the Central Dauphin School District webpage that I've created for 3D printing resources. Here you can find some information that I've just accumulated through my own experiences, and hopefully something here can be useful for you. I also have this PowerPoint presentation and this screencast up on this website. Last year, walking around the PETE&C conference, there was a lot of buzz over 3D printing, and I had just recently built a 3D printer from a very rough kit, and I thought maybe this would be a beneficial thing for some other people to see. So to start out this presentation, we'll just run through quickly the 3D printing process and how it works. You're designing your three-dimensional parts in a program like SolidWorks or Onshape.com, which is a relatively new website. It's actually a free online, almost identical version to SolidWorks. You can design in AutoCAD, SketchUp, Blender, anything you want to that you can export an STL file format from. From there, you're going to process your part in a slicing program. So basically programs like Slicer, Simplify 3D, Cure, there's a bunch of other ones out there also. They process your design and create a G-code file from your part for your printer, and it slices it up into whatever layer that you set it for. Say your layers will be 1/4 of a millimeter thick. And Slicer's a pretty good program. That's the one that we use for this. And then you actually just print the part. So you're going to use a program like Pronterface Print Run to run from a printer, run from a computer to your printer, or you can actually, a lot of these printers will allow you to save to an SD interface card so you can run your printer as a standalone device. That's how we run ours at school. That way we have 2 3D printers right now, and then we don't have to worry about tying up a computer for hours processing one file. We save everything directly to an SD card and then just take them to the machine. A little bit of history about 3D printing. 3D printing came onto the scene in the mid-1980s called rapid prototyping technologies, but they were more geared for industry. I know for the last 10-12 years I go to technology conferences, and you would see 3D printer displays by vendors, and they started out $20,000 for a machine, which was a little bit out of the price range for the high school to justify trying to buy one of those. And as years went on, they came down to $15,000, then $10,000, and the ones that you can buy already assembled today are $3,000-$4,000. But then basically in 2004, the open source movement called RepRap was developed, and they made 3D printing more affordable for everybody with open source designs and open source materials and open source electronics and circuitry. So all of a sudden you saw affordable 3D printers really under $10,000. First one in 2007, launched by 3D Systems. By 2009, the first kit forms were available on the market. Launched from Bits from Bytes and MakerBot were the 2 main ones that were out there for under $2,000. So all of a sudden in 2009, 3D printers became pretty affordable for schools. And about 6 years ago, I was looking into purchasing one for the school, and what you saw available here would be the Bits from Byte version, the Rapman printer. Had about a 7.5 cube printing area. Its base price was $1,400, and you could add a second extruder to it. 2 extruder models, so you could extrude 2 different type of materials, or PLA in one and ABS in the other, or 2 different colors, for a little under $2,000. MakerBot was also on the scene with their Cupcake CNC, and this was their version of their first printer. But it could only print about 4x4 by 5 inches, and it was base priced at about $800. So when I'm looking at both of these machines, gee, which one did I want to buy? You had the one that was really clean looking with nice steel and plexiglass design, or this zip tied together plywood model with lots of wires hanging out all over the place and a smaller build. So I thought, well, I'm going to go with a nicer one. And little did I know there would be some problems with this. The extruders are very slow to heat up. You really couldn't print two two colors at the same time, it would take 10-15 minutes just to heat up the extruder, but the circuitry could only handle heating one at a time. So if it had to keep switching back and forth between extruders, it would print one layer and then it would park itself and take 15 minutes to heat up the other extruder, and then do a little printing and then park it again to heat the other one back up, and it was a little annoying. And as of last year, the extruders were dying, the electronics and the display screen were dying, and it was time to come up with a new solution for things. So I started looking at some of our other options. At the time that I purchased this, I knew nothing about RepRap. I just knew, hey, here are two 3D printers. Little did I know that these were based on RepRap designs. And that's why they were so cheap. The companies were creating their own electronic circuitry for it, and making some modifications and selling it as their own thing. Well, today's 3D printers, and you can still buy some kits, but a lot of companies got away from it. MakerBot doesn't make them anymore, but they survived. They actually have grown to flourish to be number one of the top manufacturers right now. Bits from Bytes, they no longer exist. Today's 3D printer kits, you can actually go to Walmart and buy yourself a small 3D printer kit for under $300. These two models are actually from a vendor that I've had some dealings with on eBay, a Chinese company. In fact, the Prusa i3 that I have at the presentation today is actually this model. I'm looking at purchasing one of these Castle Minis, which are a really neat tripod design, and here's a DaVinci that has a nice enclosed case for about $500. So kits have come down quite a bit. So you're going to ask yourself a question: do you want to build a 3D printer? Well, here are the 7 easy steps for building your own 3D printer. Step number 1, you have to determine what type of printer you want. So you have to look at a little bit of the history and what's available. There are actually many different available types of 3D printers. Stereolithography is one that's getting a lot of attention these days, where you're basically using a liquid resin that cures when a laser beam hits it, and it basically builds the layers that direction. And they're advertising one of these stereolithography machines where they're pulling it up out of a bed of liquid resin, kind of like they're comparing it to the Terminator 2 movie where the guy came up out of the liquid resin. The fused deposition modeling is the most common one you're going to see today. It's the one that I'm demonstrating here, the ones that we have, where you basically have a roll of thermoplastic material, either PLA plastic or ABS plastic. They look like weed whacker line on a roll, and you're extruding it through a high temperature extruder, much like a hot glue gun, only much more accurate and precise. Then you're building it up a layer at a time. And then there are some of these other methods in here: selective laser sintering, selective laser melting. Here you can actually mold different types of metals. These are more industrial grade and much more expensive. I don't believe there are many schools that would even be able to afford these, but you can melt glass, metal, and cure them in certain ways. Electron beam melting, again, you're heating the materials and bonding them together. Laminated object manufacturing has been around for a while, and they were trying to sell these to schools about 10 years ago. Basically, you had to roll a material and it would cut out your layer and glue it to another layer. But in my opinion, this would be a lot of wasted material as you cut out the holes in each layer, and it becomes scrap. And here's a website where all this information came from. So these are the two types that are most available and what you're going to probably see in schools today. The stereolithography machines. Formlab is the one that's becoming a very popular one right now. Again, pretty high priced, and you can't get these in kit form, but it pulls the liquid resin out of a bed of liquid resin, and it forms it as it builds. The PETE printer is pretty interesting. This was a crowd-funded project that started a few years ago, where for $100 you can basically build your own 3D printer, and you're using tanks of salt water where the water drains from the top down into the bottom with a layer of resin floating on the top of the salt water, and then you use the software to shoot a laser beam into it and build it as the water rises. Fused deposition modeling, again, these are some popular ones that you could see out there. MakerBot is very popular these days. But again, you can't get these in kit form. These are kind of expensive, a few $1,000s to buy some of these. So, number 2, you're ready to build this and you want to determine your budget. Well, option number 1. I don't know too many people or too many schools in this situation, but money is no object. If this is the case for you, please leave this session now and go over to the Great American Hall to speak with a printer vendor. You do not belong here. This is for schools where we have a tight budget for things, and rather than spend a few $1,000s for a 3D printer, maybe for $1,000 you could put 3 or 4 in your classroom and make this work better for your kids, because a typical 3D print is going to take anywhere from an hour to 2, 3, 4 or more hours, depending on the size of the project. The more printers you have, the more students you can have running through these projects. So option number 2, you have a budget and a desire to learn something new. Well, then you're in the right place. You're going to have to try to find yourself an inexpensive kit, do a little internet research, and I hope that this session will help answer a few of these questions. Step number 3, you're going to find your printer. So first off, you have to determine the build size that you want. Typically, most of these 3D printers on the market, you're going to build either a 7-inch cube or an 8-inch cube maximum. You can't really go much larger with a lot of these extruded plastic 3D printers, because as the layers cool, they have a tendency to warp, and it can cause problems if you try to go too large with them. You have to be careful. Some of the cheaper printers are going to be much smaller than the 7x7x7 block, so you have to watch what you're looking at and what you want to work with for your students. Do you want a standalone printer, or do you want one tied to a computer? Because as I mentioned before, builds can take hours. So if you have a 3D printer tied to a computer, it's going to be hard to do much else with that computer for a long period of time. This is why most of the printers that I've put together, I always make sure that I get the ones that support SD cards, where you can save your G-code file to an SD card, take it to the printer, stick it in, browse the display screen, start your print off of that. And then my students, when we have a couple SD cards laying around, when they process a file, they write their name, the name of the file, the printer that they're using, and on a piece of paper, and then as the machine finishes, we can process another project right away with the student not even being there. What type of material do you want to use? PLA plastic is a sugar starch-based plastic. It's organic. And ABS plastic is not organic. It's the same type of plastic you use in car bumpers. These are the 2 most common materials you're going to extrude today. PLA, even though it is organic based, I've tested this out, and if you threw this stuff out in the wild to be rained on and weathered on, it would take 5 to 6 months before it would even start to show any signs of deterioration. I soaked a project in water for an entire weekend, and it didn't even discolor the water, to the color of the plastic. So it is very durable. It is also much easier to work with. It requires lower temperatures, and it warps a lot less than ABS plastic. So think about what you want to work with, but there are some other materials you can work with. The liquid resin ones are also there for you to use. Where does your district allow you to shop? This is always a problem with most school districts, because you need to have an approved vendor, and what you might find is many approved vendors may not have many printers available, or what they have might be more expensive. If you're able to shop on eBay or Amazon or someplace like that, you can get some pretty good deals for things. So once you figure all of this stuff out, you're off. Now, some of the plans and kits. So what type of printer do you want to build? RepRap.org is all things printer related in the open source community. These are the people that got 3D printing really cheap, and their goal is to have a printer in everybody's house, just like you have a computer printer right now. You can build your own, maintain your own. The electronics are all open source, which means anybody can build them. You can and sell them. You can etch your own circuit boards. It's not like you have one source for things. So RepRap's a great place to go, and it is alive and well. And if you go into RepRap a little bit deeper, you'll see there are a variety of different models and variations of 3D printers that people have developed over the years. You'll see that the very first one is called Darwin, and it looks much like my Rapman printer that I got 5 years ago. They consider this an obsolete design. Nobody builds it anymore because there are lots and lots of moving parts, and accuracy is really hard to maintain with this thing because there is so much moving on this printer. So, there are better designs out there, and new ones showing up all the time. Some of the more popular RepRap models are going to be the Prusa i3. This is the one that you see at the display at the presentation today. It is a 4-motor system. Now the reason why I say 4-motor system is you have one motor for the x-axis to go across. You have one motor under the table that pulls the table back and forth for the y-axis. And then for the z-axis to go up, you have a motor on either side of the machine turning a screw. So you have 2 motors for the z-axis. And then you have however many extruders. You can put multiple extruders on here, but most of the time we're extruding one plastic on these. But most of the software and hardware will support 2 extruders easily. Some people have modified them to support even more, but 2 is kind of the limit for simple printing. Another model that's becoming very popular is called the Mini Console. The Mini Console is a 3-motor design, but you don't have a motor assigned to each axis. Basically, you have a motor down at the bottom that's moving in a vertical direction on a leg of a tripod, and it's swiveling this head around and moving upward to do your prints. And these are very popular right now. In fact, I'm trying to get some funding right now to go and purchase one of these next. Vendors. So, where can you go to buy this stuff? As I mentioned before, many district-approved vendors may be more expensive with fewer options. At least that's what I found with our own school district. Amazon and eBay can offer cheaper kits of equal quality. And right now it's gotten to the point where the quality of the 3D printer is the same as the $4,000 ones that you will buy. The thing with the $4,000 ones is you're getting it already assembled, which is a big part of the assembly costs. And they throw in a bunch of extra bells and whistles, like a really nice professional looking cabinet possibly, and maybe even a little webcam on it so you can watch it printing it on the internet. That's some of the stuff that's really, giving it extra bells and whistles. But the printers are pretty much equal quality. A possible vendor that I've had good experience with is Chowhee Electronics, who sells on both eBay and Amazon, and I've posted a link there in the PowerPoint to their store. I hate endorsing a specific vendor, but we have purchased 3 complete kits from this company, and I've purchased a lot of other electronics to modify our old Rapman printer. And I've had excellent success with them, and their communications is excellent. If you post a question to them, they are back with you, by the next morning. So, they're reliable. I know that they're pretty reliable to deal with. Okay, so now you're up to step 4. You have your kit. Take a deep breath and start your assembly. Find a good set of building instructions. If your machine didn't come with them, look on reprap.org or on YouTube, and you will find lots and lots of instructions to put them together. The kit that I purchased from Chowhee Electronics did not come with instructions, but it came with a link to the RepRap website to follow their instructions to put it together. And there were some minor changes and modifications to their printer from the instructions, but they were easy enough to determine what was different. Take careful measurements. Accuracy is key with these. If something is supposed to be set to, you're supposed to screw something together and it's supposed to be 12 millimeters apart, try to get it there as close as you can. When you're putting it together, make sure that you can move all axes freely by hand before you connect the motors, because if there's any binding or something's not, your rods are not parallel to each other and the carriage doesn't move well, you want to fix that before you hook it all up. Follow wiring diagrams and programming instructions. There are a lot of wires to connect. It can seem a little intimidating, but there are a lot of guides out there to help you put it together. There is very little soldering to have to do to these kits because everything is set up to be plugged in with little electrical plugs, so pretty easy to put together. Determine the firmware you wish to use. The firmware is the software that controls the printer and interprets the G-code file. So basically you design your part, you take it into a slicing program. The slicing program creates a G-code file for your printer. The firmware is the software loaded on the actual printer that can interpret the G-code and move the motors the way that they're supposed to move. The vendor may provide you with the programming, which will make it very easy for you. But if it doesn't, it's not the end of the world. You can download some basic firmware files and modify them to your printer relatively easily. So here's what the typical electronics in a 3D printer involve. You have your stepper motors. Depending on the type of printer you get, will determine the number of stepper motors you have, how many extruders you have. A stepper motor is a motor driven by a digital pulse to rotate a specific degree angle. So when you take a stepper motor and you give it a pulse, typically these motors are what they call a NEMA 17 motor, and that means they're 1.8 degrees per step. So if you give it one pulse, it's going to move 1.8 degrees, and any multiple of that, you know exactly how many revolutions that motor has turned. That's what has made 3D printing an accuracy, and even the printer that you use at home on your computer uses this type of technology. Another thing that has become very popular in recent years is using a heat bed. The old first generation 3D printers, my Ratman printer that I bought 5 years ago, did not have a heated bed, and the purpose of the heat bed is it gives you something else to help the thing stick to the table a little bit better. You heat the bed up and it keeps the part heated to help minimize warping and make it hold fast to the table better so it doesn't pop off. Typically, sizes of these heat beds are 8 inches by 8 inches. They typically run on 12 or 24 volts, and you can heat them to 100 degrees Celsius pretty easily and quickly. I know on 12 volts I can heat the 3D printer that's here to 60 degrees for PLA plastic in about 5 minutes. It takes closer to 10 to get up to 100 degrees for ABS plastic. Now, the typical electronics that drive this thing run off the Arduino open source electronics system, and Arduino electronics are used for a lot of hobby electronics. So basically the parts of this whole 3D printer system is you've got the Mega 2560 board, which is the small blue board down here. This is the microprocessor. This is the heart of the computer and where everything occurs. When you load the firmware in, the firmware is loaded into this part of the circuitry. There is a USB cable connection on it, a power connection, and this is the heart and the brains of the whole process. Now, what turns it into a 3D printer is the RAMPS 1.4 board. This RAMPS 1.4 board just plugs right into the top of this processor, and this is what turns it into a 3D printer. Here are your connections for your 12-volt power supply that you need, and you actually plug in the heat bed, your extruders. Everything has its own connection points on this board. You have these things called stepper driver boards, and these little tiny boards are used to control each individual motor, and they plug into the board on the top here. And the nice thing about everything being modular like this is if you happen to have a board burn up on you, one of these little stepper driver boards, eBay, $3, $4, $5. You can just buy a new board, yank the one out, plug a new one in, keep going. You know, everything works out great. If this board were to be damaged or destroyed, $5 for this board. The Mega 2560 board, that's going to be a little bit more expensive, but these are what you're going to see on almost every 3D printer. Now, if you want your printer to be a standalone printer, you want to make sure that you get one of these 2004 LCD controller boards. It has a display screen, and on the back corner of it is an SD card reader. If you don't want your printer to be standalone and want to keep it plugged into a computer all the time, you do not need this. It's kind of an extra thing that comes along with the kit. There is also another type of board. I don't have it listed here, and I forget what the number is, but it's more of a square board than rectangular. And it has a little selector button here that you rotate it to browse through your menus, and you push it to select something. It's really all it is. So these are the things that you want to make sure you have. And all this kit, all this electronics together typically runs about $30 to $50. So it's not that expensive. It's actually pretty cost effective. And like I said, you burn one piece of it. Everybody is making this stuff. It's easy to find a replacement. And here's what it all looks like being assembled. So you've got the Mega 2560 board on the bottom. Here's the RAMPS 1.4 board, and then all the motor controllers. Now this is set up X, Y, and Z and one extruder. If you had two extruders, you'd plug a second stepper driver board right into this slot here. Now there are some alternatives to this, and there are quite a few out on the internet. This is a popular one right now called the Rumba AT Mega board. Basically what they've done here is they've combined the Mega 2560 board, which is kind of right here, with the Ramps 1.4 board here. Now this particular board still needs all the little tiny motor controller boards to plug into here. Some of them that you find on the internet have them soldered and integrated right in with the system. My concern with this is this board alone usually runs you about $50, so if something burns up on this, you know, it's a little bit more expensive to replace it. But you know, that's why I prefer the system that was before this. Now when you go to wire up the Ramps 1.4 board, here's a diagram to kind of show you what everything connects to. Unless you have some notes with it, this is a little confusing to read, so I prefer this next diagram a little better. If you notice, it shows you extruder 1, extruder 2, here's the heat bed and the wiring for it. There's the thermistor that tells you what the temperature of something is. The extruders have that as well. Here are the stepper motor connections. You'll see that everything is color coordinated, so all you got to do is just match up the colors and plug them into the boards. Then a plug to the power supply. This actually makes it pretty easy, but you still have a lot of wires to deal with, so it does take a little time and a little caution to make sure you get everything where it's supposed to go. Now the firmware. Marlin and Sprinter seem to be the most popular firmwares that I found out there on the internet. They are written and downloaded through the Arduino programming software. So remember that Arduino Mega Board is the processor for the whole thing, so obviously it has to work with this. Well, first you would have to download the Arduino software from this link here. And then you would either need to find a compiled copy of a Marlin or Sprinter software for your printer. And there's a lot out there on the internet for most of these models. I'm using Marlin. It seems like it was pretty easy to work with and a lot of people recommended it. So once you find your firmware, or hey, maybe even better, you'll get one from your vendor that's set up exactly for your machine. But if you can't, you can customize this firmware however you need to for your machine. It is reading a lot of code. It looks a little confusing to try to run through it all and make sure that everything is proper for it. But there are several websites out there that I reference later in this presentation that will help you with all the adjustments that you need to make. So it's not that bad. There are a lot of tabs, but everything is pretty much on one tab that you're going to make all your modifications on. Download the firmware to your printer from your computer, and it'll be saved into that Mega 2560 board, and you're ready to maybe start testing out your system. So that brings us to step number 5. It's time to calibrate your machine. Your machine needs to be tested and checked before that first print. I know you're anxious to print it, but you want to make sure that if you tell the X direction to move 100 millimeters, it really does move 100 millimeters. Same for the Y and the Z directions, and also for the extruder. If you tell it to extrude 20 millimeters of filament, you got to make sure it's really extruding 20 millimeters of filament. And that's also going to be determined by the nozzle diameter, because most of the filament these days is going to be 1.75 millimeters in diameter, about the thickness of a nice heavy roll of weed whacker string. And the nozzle that's screwed on the bottom of your extruder, that's actually putting it down on the table, is typically going to be 0.4 or 0.5 millimeters in diameter. That determines a lot of the settings for your printer. And as I mentioned before, there are many websites and YouTube videos out there that will walk you through the process of calibrating your machine. So be patient. You might need to adjust your firmware and re-download it several times to your 3D printer till you get it right. So it might take several attempts to do that, but once you get it there, you won't have to worry about it again. You'll have it. Now you're up for number 6. Step number 6 is to set up your slicing program. The slicing program that we use is called Slicer. There are several slicing programs out there that are recommended. I personally prefer Slicer. It's a nice one and very easy for the students to work with. Your slicing program needs to be set up for your printer and your filament. Most programs will have a basic setting for you that you only need to tweak a little bit. And again, I'll bring up Slicer at the end of this PowerPoint to show you how it works out. Some of the basic things that will need to be set on your slicing program will be the size of your print bed, because every print bed's a different size, so you want to be able to set that up. You'll have to set up your nozzle diameter, and I put in there 0.4 millimeters because that's what I use, and that seems to be the more typical size these days. Your filament diameter. There are still some printers out there using 3 millimeter diameter filament, but most of it these days is now 1.75. In fact, it's getting harder and harder to find 3 millimeter filament. Our original Ratman printer used 3mm filament. When I redid all the electronics, I took it down so that it works with 1.75. You have to set your filament temperatures, typically somewhere around 200 degrees for PLA material, around 250 or 260 for ABS. You're going to have to set your print bed temperature, typically around 60 degrees for PLA, around 95 to 100 degrees for ABS plastic. And you want to set the number of extruders and the distance between them so the computer knows that if those extruders need to line up in the same location, it knows what the distance is between them. And one of the more important things you want to set is also your infill percentage. You don't want to make your project solid plastic, or you're going to go through a lot of plastic. I have my infill set to about 20%, which basically means everything we print is pretty much hollow. And then number 7, your time for that first print. So you're ready to figure out the thrill of victory or the agony of defeat. You're going to want to process an STL file in your slicing program and take it to your printer. Pick something simple for your first print. I know this picture shows a very elaborate Terminator head. Pick something simple, maybe even like a cube that you know what the size of it is. So pick that first object you want to print. Print it out, check everything for calibration. Make sure that if that brick is supposed to be 20 millimeters long and 20 millimeters high, it really is. So check it all out. If everything goes well, you're ready to start printing. If you need a model to print that is already in the proper 3D printer format and you don't want to make something yourself, you should check out a website called thingiverse.com. This website is actually maintained by MakerBot, and it's basically a community website where anybody and everybody posts 3D models that they've created. So it's a good place to go for things, and I've actually even shared all the models of my Ratman printer modifications up there because I had to make a lot of specialty parts for the new carriage, and I've placed them up there for other people that might have an old Ratman to be able to use them. So we've hit the point where even after you have your 3D printer together, you're still going to have moments where it's going to cause some headaches. Most of the time you're going to want the good, meaning that you walk in the next morning after your printer was running all night long and you see a nice project that a student designed that might look like this, where they did a little star puzzle block and it prints out well and it all looks good. Now, not only do you also have the good, but sometimes you'll walk in and you'll see the bad. Here's a product of an iPhone stand that just didn't finish. And even worse, you're going to see the ugly. And boy, I tell you, sometimes it gets really ugly if your part breaks loose from the table and it just starts spraying plastic all over the place. So you want to try to avoid that as much as you can. Even when you take all precautions, a project just may not stick right, or it might be designed in a way that doesn't give it a lot of surface area to stick to the table. So that's what happens. Now, as I mentioned before, I have some resources available for you, and if you download this PowerPoint, you can just click on all the links here. One link to the RepRap source, one to a Marlin user's guide setup, and a second one that'll also give you some more information that the first one doesn't. I have a link to the Prussia i3 assembly guide, a link to Thingiverse, the 3D printing community. There's a really good YouTube video I found on calibrating your 3D printer that I have up here, the Arduino website, and here's a RepRap page on connecting up the Ramps 1.4 board. Here's a nice website also for filament and motor calculations, just in case you got to figure some stuff out and like how much does it cost to do a project. And I also included again the link to my 3D printer website and a link to the Slicer website. Now, if I get out of this presentation for a moment and bring up the internet, some of these websites we were looking at here again is that 3D printer resource page that I put together. Slicer would be this, slicer.org. Notice there's a 3 in place of the E. This is, in my opinion, one of the best 3D slicing programs out there to download, but again, you can use what you wanted to use. There are several choices. Here is that one link to the Marlin firmware guide that talks you through setting this up and what settings would need to be customized for your own personal 3D printer, and even setting up a lot of the mechanical settings. And here is the link to the Prussia i3 build manual, and again, it's just screwing a bunch of stuff together and making sure that everything is put together correctly for you. So those websites are pretty good. Slicer would look like this, where you customize it to fit your table sizes. They would be under printer settings, where you set up like how thick you want your layers to be and how many shells you want to go around the outside. Here would be your infill, and you can change what your infill looks like. If you want something to have a good bit of strength, there's a honeycomb fill, which looks pretty good. Speeds might be another place to go. I played around with the speeds of the machine. You know, sometimes it might seem like they're going a little fast or a little slow. I like to slow down the first layer and extrude a little extra heavy plastic for that first layer, so it helps stick to the table better. In your filament settings, there's where you would set the diameter of the filament, number of extruders, the table and filament temperatures, how hot do you want it to be. Then under printer setting, this is where you would set your nozzle diameter. And you know, if it's going to extract any extra plastic, and even if you wanted to play around with some custom G-code in here. Now I'll go back to the platter and I'll add a model right now. And I'm printing a monkey head right now over in the corner of the room, and I'm going to bring up that model on the screen. There's the STL file of this monkey head. And you have some different ways that you can look at it. Here you would set up your printer, and if I looked at it in 2D, man, I gotta kind of move it around here a little bit. Okay, there's 2D. It tells you how much area it's taking up. And if you go to the preview menu, here you can actually see how it would build each layer. And if you wanted to see it in a two-dimensional layer, here would be the two-dimensional layers for it. And when you're all ready, you would export G-code, save it to an SD card, and it would create the file to go to your printer. And that's really about it. So thank you for attending this session. If you have any questions at any time, please feel free to email me and I'll try to help you and direct you in the direction you need to go with things. Jay Chronister at cdschools.org. And good night. Thank you.